Okay, we need to take a couple steps. Well, not a couple, actually around 10 steps to get the image properly generated in front of our eyes. First step, placement of the eye. Obvious, right? Well, you place it either on one side or on the other side. Second step, creation of the line of vision. In other words, the optical axis. It comes right out of the eye. It's the vision, line of vision. Okay? It's literally as if it's coming right out of the eye. That's, by the way, probably a reference to the older view of vision of optics. Before Isaac Newton, we thought that eye were emanating light. 3. Well, what are you looking at? Placement of the object. Where's the object? Well, along the line of vision. Somewhere on that so-called optical axis. Okay? What's next? Well, we're talking about image formation through lenses or mirrors, right? Here, thin lens, or a mirror. Okay? So, pick your device. I would say, pick your glass. Maybe that sounds even better. Now, actually, when you pick it, or when they pick it, or anybody's picking it, right? Of course, most of the time, most of these things will be already given to you in the question, in the textbook, or by a teacher in the classroom. But you understanding the algorithm, step-by-step process to get that is important too, because that will make your life easier when you deal with those questions, right? So, object, pick your glass. What do we have? Mirror or thin lens? Right? Which one do you pick? Well, first of all, let's see how they look like. Mirrors. What do mirrors do? Right? Mirror. They reflect light backwards. Reflect back light. Okay? Lenses. What do? They pass it through, but refract it. So, deflect it slightly in its direction, in its angle. Now we got two kinds for each. Mirror, look like that, look like that. Right? Depending on which way light is coming from, it will do its job. A ray of light comes from here, it will be one story. If a ray of light comes from here, it will be another story. Same here. If a ray of light comes from here, that's one story. If a ray of light comes from here, that's a different story. Okay? That's very important. Because two sides of that kind of a curvature have completely different curvatures, right? It's kind of inside out. 180 degrees different. Now, lenses, like that. What do you see? Like that. See? Also got an inside out version. Now, after you know which one is which, you pick one, and you place it on the optical axis appropriately. Appropriately in this case means proper to your goals, your aims, right? Your purposes. What's the purpose? What's the purpose of placing a mirror? Purpose of placing a mirror is to see the reflection of something between you and the mirror. So if you place a mirror like that, then the rays of light going from the object, reaching out the mirror, will bounce back in a certain direction. But if you place a different mirror in the same kind of a situation, then rays of light coming from the same object even, reaching up to this differently curved mirror, invertedly curved mirror, will go backwards in a different way, will reflect back in a different way, right? And basically, the whole idea of how those rays of light will reflect is governed only by one rule. And that is the rule. The optics rule. What is the rule? All rays reflect at 90 degrees to the surface. Okay? That's all that there is. Where's the 90-degree angle? Here it is. It's a 90-degree angle. What about this? You see how it went? It's a 90-degree angle. What about this? That's a 90-degree angle. It's a 90-degree angle. All at 90 degrees. That's how you know whether the light will be coming back into one place or going away from each other into two different places. Converging, diverging. But look, if you place your eye here, and there was, let's say another eye. That was you, somebody else is looking. And let's say the mirror has both of its sides being reflecting, some surface that reflects. Say there was another object here. What would happen to this situation? Well, the rays of light this time are going to be behaving. These rays of light coming from this object to this eye will look like they're actually focusing in one place, converging backwards. Right? So, from this perspective, that's the same mirror as this one. Maybe I'll give it a little bit of a dimension here. Okay? So that's the important thing about mirrors. Don't learn it by heart. If it looks like that, it's the diverging. If it looks like that, it's converging. No, it's not just how it looks like. It is the 90-degree reflection to the surface and where your eye is. There's two sides, right? Every side generates one of the two behaviors. So every mirror is diverging and converging depending on where you look at it from. Okay? So, now this is first 5 steps. Let's go to the step number 6 and 7 and 8. What do we have there? Step number 7. Know the center. Where's the center? For mirrors, the center is the center of the circle created by the arc of the mirror. Well, the mirror is like an arc, right? Arc looks like that, right? Well, that's the same thing as that. So, place an eye, mirror, object, continue the curvature of the mirror, and there we are. It's there, the center. The center is always on the optical axis, somewhere on the optical axis, we should say, right? It is somewhere, it's gonna be somewhere on the optical axis. Okay? It's one case. Case A, what about situation where you're not dealing with this kind of a circle, but that kind of a circle? Well, nothing really different, same thing. Just extend the curvature and you will get the unrealized circle realized, and therefore you will see where the center should be, right? So that's the localization of center for the mirrors. Now, what about lenses? Lenses are not circular structures, right? So the center is right in the middle of that structure. The center is right inside. Halfway in, of course, right? The middle. And I place. Now, we didn't talk about this. If I place my object here and then place my lens there, that makes no sense. I use lenses to see something on the other side of the lens, right? See things through the lens. So the object should be there if my eye is here. You see that? And the center is right in the middle. Also, always, somewhere at the optical axis. That's true for all of these. For that, for this. Sorry, I should have not done that like that. It is true for mirrors. It is true for lenses, right? Now look, if I put my eye now here, this situation will make no sense again. I am using lenses to see through them. So the object should be on the other side, right? Now another case of a lens is the lens that doesn't look like that. That looks like inside out version of this. Again, something like that. Again, center is right in the middle because of these guys. Lenses do have some extension. They do have some width to them. So you can pinpoint the center right inside. And again, if I place my eye here, the moment you see, remember, the placement of the eye was the very first step. The moment you place your eye, now you can figure out which placement, what kind of a placement of an object will make sense and which one will not make sense, right? Depending, of course, not only on the eye, but also on the device you're using, which was like the third step. Well, again, if it's a lens, the object must be after it, right? It must be further away from your eye than the lens. I guess you understand what I'm talking about. Another situation, the moment you place your eye on the other side, and let's say here we are, again, the lens, the center is right in the middle, right halfway in, the object must be on the other side. Otherwise, again, it makes no sense. Now, let's get to this is true, right? Somewhere this is true for all of them. That is true for this, and that is true for that. Now let's get to the last couple steps, which will allow us to actually form the actual image, to get to the last piece of this beautiful step-by-step algorithm to get the relative positioning. Not only positioning, but also the size. And of course the location of the image formed using 4 different kinds of glasses. Alright, okay, so 8th step. What is the 8th step that we do now? We place the object, we got our devices, now we know the rule. Remember the rule, 90 degrees to the surface. Already now you also found the center, you know where the center is. Now you have to locate the focus. Locate the focusing point. Focusing point. The focusing point is always somewhere on the optical axis. Now, if you are using a mirrors, what's happening is that it's basically geometry, and it happens to be the case that focus is positioned halfway in between the center and the surface of the glass. So mirrors, for all mirrors, focus is halfway in between the center and the surface of it, of the mirror. Okay? So what does that look like? It looks like this. Eye, mirror, an object. This mirror has that kind of a circular structure. If you contain it, if you extend it, center, and right halfway in between the center and the surface of the glass, there's a focus. Okay, that's important. That's true only for mirrors. For lenses, unfortunately, we don't have that kind of a relationship. By the way, this relationship can be written down in terms of distancing as C equals to distance to C. Let's say C distance equals to, well, double of the distance to the focus, right? Okay? Important to know. Lenses, unfortunately, as we said, it's not the same kind of situation. Obviously, because the central lens is right inside the lens. So how can you have a focus inside the object? You're supposed to be using that object to see, not to have an image stuck inside of it, right? Okay, step 9. What we do? Locate the focus again. This time, focusing point and focus, same thing, right? This time we're talking about lenses. Okay? Now, with lenses, what's going on is this. You really have to remember that the axis, that the light that is going to be coming from the object towards the lens will be refracting from it. And by the way, you have to extend the ray of light right up until the middle of the lens, inside the lens. And then you can start thinking about how those rays of light will refract. Refract doesn't mean reflect. Reflect means go backwards. That's the mirror job. Lenses pass through the light, right? So you must be somehow seeing it at the end of the day. Now what happens with this kind of a structure if light comes from here and reaches out to this kind of a surface on its way? Well, what happens here, it's again something like the same thing, something like the previous rule we talked about, the main rule of optics, right? Rays of light will behave as if they're following the 90 degrees angle that is made with the surface where they touch it. So considering that the ray of light will start changing its behavior somewhere around the middle, inside the surface of the lens, in this case, considering that it was first experiencing this kind of a surface, the 90 degree angle to this kind of a surface is something like that, right? So that's how it's going to go. It's going to go like that. Same will happen here. See? It's going to go like that. So, this is the situation. The focus fundamentally is defined to be the point on the optical axis where all parallel to that axis rays eventually go and gather focus. So all rays of light that are parallel to the optical axis, you can see, right, all of them, they will gather in that place called focus. Okay, that's the definition of the focus. Very important. Okay? Now, let's look at the other guy. So we're locating the focus, right? Now, let's look at the inside-out version. Another lens. What's going on with that lens? Well, and let me just on purpose put my eye here, right? Let's see what's going to happen. Oh, this one is, okay, whatever. Let's just keep it like that. Straightforward. Here, what happens? So I place my lens here. Center's right there, okay? I must be having object on the other side. Let's make it like that. Okay, the object. Okay, that's the object. Oh, what happens? The rays of light go up until the middle. And then what do they do after that? Well, they gotta be passing through. How are they gonna pass through? This time, you see, the first layer, the first surface the ray of light gets in touch with, it's like that. What is the 90 degrees to that kind of a place? Well, it's like that. It's gonna go like that. What about here? See? Like that. It's gonna go like that. What about the ray that goes from here towards here? It's like that. See? It's like that. Something like that. Same here. See? 90 degrees would be, oh, actually this way, a little bit this way. Kind of, right? Something like that. And you must say, what is this? Where are they all going? They're definitely going to different places. So how are we going to find the focus? Well, just like in the previous case with the mirrors. Actually, I didn't show you the previous case with the mirrors, but it's good time to know it. What happens, what we do in cases like this, is we say, it's okay. Just imagine they have a virtual mirror version of themselves attached to them. Just extend that direction backwards. And you will see that then they will definitely meet one place. And that would be the focus. Okay? So you see, this is still the main focus, but it's now the focus that is in the virtual part. Or on the virtual side. On the virtual side. It's not in the actual, it's on the virtual, right? Here, this focus is on the real side. We didn't have to imagine anything. We just use the actual rays of light. These ones, these extensions, are not the actual. They are the virtual parts, virtual segments of the pathways that the rays take. Okay. Well, now given that I didn't show you the previous, that kind of a case with the mirror, I'm going to show you now that kind of a case with the mirror. One is, when do we have to extend the actual rays of light in order to find the main focus in the case of mirrors? So that's like the previous thing. Remark. In the case of a mirror like that, which will definitely push the rays of light away in different directions, still of course at 90 degrees to its surface where they touch, to the direction of the surface at the very place where those rays of light touch it. Still, the problem is that all those parallel to the optical axis rays of light reaching out to the mirror, they will all reflect away. They will all reflect away. You see what happens? They will all reflect away. Even the one that's going exactly along the optical axis will still reflect backwards. And it will all seem its own. There's no like focusing, no gathering, no convergence. That's why we call this the diverging kind of a situation. But again, to our help comes the fact that we can extend all these ray paths backwards into virtuality. And here we go. If we do that, we'll find a position where all those rays of light could potentially meet in the virtuality. And that place, you see, if I've drawn everything correctly, that place will match with the fact that the center must be double the distance. Now, okay, right, I'm not perfectly drawing things, but you get the point, right? That it will, if I did indeed drew everything perfectly well, if I was using all the machine, the machine was doing it instead of me, protractor and stuff, it would have been, actually not using the black here, it would have been the case that the center did end up looking like it is, right? Somewhere halfway in, exactly halfway in, right? Between the surface of the glass, the mirror, and the center. But imagine I did draw it correctly. Something like that. It's more or less, it's better, I guess, than the previous picture I had. And here, it becomes kind of justifiable, right? That's the center. See? That's the center. That's the focus. Double the distance. Makes sense. Okay, now this focus is also, as you can see, on the virtual side. And obviously the center is also on the virtual side, right? Don't worry about the center. Why? Because we'll see that we only need to know the distance from the glass surface to the focus when we are going to decide the location of the image. And we'll also use the distance between the object and the surface, together with the distance between the surface and the focus. But we will have to assign proper signs to those distances, where all the virtual situations, virtual distancings, will be assigned the negative sign, and all the real distancings will be assigned positive sign. Okay? So we'll call the distance to the focus small f. We'll call the distance between the object and the glass surface s. And we'll call the distance between the glass surface and the image created s prime. Now, where is the image? Last step. After you understand how to find the focus and you know how to locate the center, you can now do one last thing, and I think that's the step 10, 9, whatever. Next step, final step. Form the image, finally. Find the intersection between the following two rays. First, the ray or a ray in your ray that eventually goes to the focus. We know which ones are those. In your ray that eventually goes to the main focus. And another one, the ray that goes between the object and the center. I should say that it extends, let's say, because sometimes you have to draw it as if it's going from the center towards the object, but because we're dealing with the geometry, we're interested in geometry only here, we don't really care about the actual physicality. Remember, the virtuality can help us. So the ray that extends between the object and center. Very important. So, the center, right? Still have enough space here. Okay, so what do we do here? How do we do it? Okay. Hey, let's do this. An eye, optical axis, the mirror, the object, that's the mirror, the center, figured out. Now, well, I picked this position. That's the ray of light that goes to the center. Now it does, eventually, this is the surface, right? The actual surface. When it actually reaches out, bounces back and goes like that, right? Same direction. Now we know where the focus is. We're lucky, it's a mirror case. Right in between the center and the surface. Now, the ray of light that goes from the same position on the object that you use to draw the direction of the ray of light going to the center. Now you have to be always starting from the same position on the object, right? Because you're trying to see the image of one thing, of one particular part, of one object, right? Or one portion of the object. You're not trying to talk about different pictures, pictures of different parts of the same object. You can't see, right? Every position is responsible for one piece of the object in vision. So, starting from the same location, you can start here, anywhere you want to start from. Draw the ray of light that goes to the center, do the reflection, whatever, even if it was refraction with the lens, it will still go in the same direction. The rays of light that go from the center to the center never change their direction, okay? No matter whether they are reflected or refracted. And now you gotta draw another one, because you need to find the intersection. It will be the place where the image gets formed. The intersection of these two kinds of rays of light. Okay, now draw the one that goes through the, oh sorry, my bad, I'm being too simplistic here. We know that rays of light do not go straight to the focus. They reflect or refract back to the focus. Right? See? Something like that, right? Probably here. Again, pictures. I can't draw pictures that are ideal, but you can see that this one's going to reflect somewhere here, reflect somewhere here. Okay, that's fair game. That's kind of the middle. And that's kind of fair game too, right? This is like almost 90, right? So, now, but what happens? Oh, you see? Well, unless I extend my this ray of light down, I'm not going to get the intersection. Now I get it. Here we are. That's where intersection got formed. So what is this? Well, if you connect this point with the point directly on the optical axis, you will get the image. That is the image. Okay? Image got formed. Here we are. It's very close to the focus, as you can see. And it's inverted, right? Again, it's halfway in. And what we're talking about now, you can say, we're picturing the image that is halfway, could have been extended like that, or it's inverted, right? It's inverted. This part, you can talk about this part has become this part, right? This part has become this. This is still this. You see what I'm talking about? If you extend this one, it will be backwards. It will be generated there. So if I draw this part here, if I fill it up with the red color, which looks like pink now, what will happen is that you will get the same relative sizing, the same location, the same relative positioning, and it will be upside down. You see what happened? Therefore, no matter which position, which place you start from, you will get the right answer for the image location. And the relative sizing, right? Symmetrical, right? And the location, positioning, the black side became down, red side became up. So what we have here, therefore, we can create some intuition towards the next chapter in our understanding of the localization of the image, which is to measure the positioning, the location, and the size. We can finalize our claim here and say that what we'll learn here is the following. Learn facts. What are these facts? First of all, the image may get upside down. The image may get inverted. Second, now we didn't see this guy becoming created on the virtual side, but look here. Center, here, reflection, right? This position, this guy. What happens? Where do these two rays of light get intersected? Right? Here? The images form here? What is this? Isn't that the virtual side? It is. So, it may form on the virtual side. Okay? And the third, it may change its size. It may resize. Very important. It may resize, it may form on the virtual side, and it may get inverted. That's it for now.